Good morning, Astronomy 1010. Today, we're going to continue lecturing on some last little bits having to do with Newton's laws, tides, gravity, escape velocity, and then we'd like to move on to talk about the nature of atoms and energy and some other concepts like that. So today's going to be a real mixed bag of physics concepts that we need to cover for our exam, which will be coming up in a week or so. That's something to be thinking about, right? Today, we're going to do a lab on the practicing, once again, using Newton's version of Kepler's third law. And this lab is easy and fun. And you just need your calculators and a paper and pencil. And it's good training for the exam because you'll have to do a problem very similar to that. So let's get into it. In our last class, we spent the end of our class learning about Newton's versions of Kepler's. Oh, wow, they changed things here. Okay, there we go. So in our last class, we learned about Newton's version of Kepler's third law. And what is the concept behind Newton's version of Kepler's laws? Do you guys remember anything about that? What do you have in your notes? What'd you learn? Someone talk to me here. Andrew, Frank, Nicole? Wow, you guys are scaring me.
He changed the Kepler's laws, like he kept the p squared, but the other side he changed it to 4 times
pi squared. Okay, all right, Matt. So you're giving me something I can work with. So what does that mean? So how is Newton's version different than Kepler's version?
It's more accurate because
it's not so much about accuracy, it's where it can be applied. Newton's version includes the effects
of the retrograde effect on the planets, or
not retrograde.
Not necessarily.
Well, what did Newton do for us? We learned Newton's laws of motion, right? And then we learned something else. What else did we learn about that Newton taught us?
Gravitational force?
Yeah, gravitational force. So Newton's version includes the effects of gravity. That's the whole concept. That's why there's a big, okay?
Yes.
Okay, maybe we better take this back a step, okay? Considering, Matt, that does help, okay? So that's very helpful. So in Kepler's version, it does not include the effects of gravity. And for that reason, it only works for planets which orbit the sun. Right? And that's p squared is equal to a cubed. The important thing to remember about Kepler's third law is that the period of the planet is in astronomical units. Oops, sorry. The period of the planet is in years. That was last night's whiskey talk. Years. And the distance is in astronomical units. Hey, who's talking to the Death Star back there? You gotta mute yourself. Let me take a moment out of my lecture to find this rude person, Harmony Lee. No, it's not Harmony. Who is this? Or is it Harmony? Yeah, I muted you, Harmony. You had to be disenfranchised there. Okay. All right. So the period is measured in years. The distance is measured in astronomical units. That's Kepler's third law. Then there's the Newtonian version, which accounts for gravity, and that works with any planetary orbits. And as you will remember, I like to call this version NK3. Okay. And this kind of works for any two orbits. Matt reminds us that the version is more intense. 4 pi squared a cubed over g times the sum of the two masses. And here the units have changed. The period is measured in seconds, the mass is in kilograms, and the A must be measured in meters. The picture that we should have, let's look at a slideshow here, is of two planets orbiting around each, or two massive objects. It could be a planet and a moon. It could be a star and a planet. But the picture looks like this. M1 and M2 are the two massive objects, and A is the distance between them, okay? So A is the center-to-center distance between the two objects. P, of course, is their period of rotation. Usually we pretend that one of the objects is orbiting around the other. Sometimes people refer to this as stellar wobble because it implies that the planet exerts a bit of gravitational force on the star as well. And this causes the star to kind of wobble on its axis due to gravitational tugs from the other planets in the system. Our own sun is tugged by Jupiter, by Earth and Saturn, and to a small degree by the other planets as well. Remember also that from your history lesson that Galileo had attempted to try p squared equals a cubed. Let's get my history of astronomy lecture up real quick. Kepler had written a letter to Galileo asking him if he would try out p squared equals a cubed on the moons of Jupiter. And Galileo, when he attempted to do this, discovered that p squared did not equal a cubed for the moons of Jupiter because they were trying to do this experiment. Okay, what's that noise? 100 years before, sorry. They were trying to do the experiment 100 years before Newton had developed his law of gravity. Newton's version could have accounted for this. Now, let's ask the class a thought question. Suppose we consider the three variables that matter in Newton's versions of Kepler's third law. If I were to write this in a proportionality argument format, I could ignore the 4, the pi, and the g as constants of the equation, and I could write p squared is proportional to a cubed over the total mass of the system. That's a sort of simplified version of the problem that takes out the fixed numbers and leaves only the variables that change in the equation. Class, what do you suppose is the easiest thing? If you were actually Galileo and you were to go out and actually try to measure either the period of the planet or the distance between the planet and the moon or the masses of the planets and moons, which do you suppose would be the easiest variable to measure? This is a level 2 kind of question here, so you have to put your thinking cap on. If you were out at the telescope and you were looking through the eyepiece, and if you could see Jupiter with its stripes and some moons nearby, what do you suppose would be the easiest quantity to measure as an observer? Period, distance, or mass?
Would it be distance?
How would you do it, Frank?
Would you have to get the mass of either Jupiter and its moons?
So I'm imagining that we don't have any of these quantities to begin with, Frank. So it's not like in a problem in homework where someone starts off just giving you the mass. What if you didn't know any of the three quantities and all you have is your telescope observations? How would you get, when you said you'd have to get the mass, how would you get the mass?
You would have to find an existing number of something comparable to it.
It turns out, Frank, that the mass is actually hard to measure. There's not a good way to determine mass just by looking at a planet, right? Usually when we measure the mass of something in our everyday life, we either use a scale or we use a balance beam is actually the proper way to measure mass. Although you can do it with a scale if necessary. You can't put Jupiter on your letter scale. It's not going to work. You can't travel out there. Frank, the distance turns out to be not the hardest thing to measure, but it's also not the easiest thing to measure. The easiest thing to measure is the period of the moon's rotation. How would Galileo go about measuring the period of a moon like Io or Europa? What would Galileo do? Could anyone imagine something? I want to hide the trolls here. Does anyone want to talk to me today? Or are you guys just real life trolls? Would anyone like to interact with the professor and make me feel less lonely on this Monday morning? Could you imagine?
Can he use the law of gravitation formula, or is that not related?
It's not a formula thing, Matt. I'm just saying you're out at the telescope and you're watching the moons go back and forth. How would you figure out the period?
Does he just have to wait till it gets back to its original position?
Thank you, Noah. Yeah, you'd start when one of the moons was at its greatest distance away from the planets, right? We would call that maybe greatest elongation. Let me go to full. Oops. So you'd start when the moon was. Sorry, guys. I'm trying to position your little faces so that the people watching later can see this. You'd wait until the moon was like at its greatest extent, its greatest elongation. And then you would take out your crappy little stopwatch, right? You'd hit start and you'd wait for the moon to go all the way across and back again. In other words, P is what we would call in astronomy the observable. Meaning this is the thing that you actually go out and measure at your telescope. Frank, you can also get the distance, but it's a little bit harder. To get the distance, what you would do, Frank, is you would measure the angular separation between Jupiter and the moon. And then you would use the small angle formula to calculate the distance. The small angle formula, which you were taught in chapter 2. So you can get the A, but you have to do 2 extra steps. You have to measure the angle first. This is an angle. And then you know the distance to Jupiter, and that lets you calculate the separation. Who knows? I might even make you do something like that on a test someday, huh? Okay, so you might want to think about that. Okay, in that case, if P is the observable, why would you ever actually want to solve this equation for P? The only reason we started off by writing it with P squared equals all this stuff A cubed is that's the form in which Kepler taught it to us. And so we're kind of cribbing off Kepler's notes. But that's not the real purpose of MK3. The real purpose of Newton's version of Kepler's third law is to measure the masses of objects. And for this reason, your book nicknames this formula. It's got a little nickname for it. It calls it the cosmic balance beam. A balance beam is what you use to measure masses. And the real value of this formula is to be able to solve for the mass. But for that reason, we have to be able to rearrange this equation for mass. So let's go ahead and do that over here on the left. Introducing a new version of NK3. I like to call it NK3 solve for mass. And you might think of this as the entire point. This is the whole reason why you've learned this formula, is so that you now know how astronomers deduce the mass of objects from Jupiter to the planet Earth itself. And it looks like this. M total, the combination of M1 plus M2, is equal to, I might have to give myself a little extra room here, 4 pi squared A cubed over GP squared. That's the real version of the formula. And you'll notice I did a little algebra there where I flipped the masses up, but I flipped the period down. Now, we did do a couple of example problems like this during our homework, but I'll try to have some more practice problems on this before the test comes, showing you how you would use this. But for now, make sure that's in your notes because that's very important.
How long is the test?
I'm sorry?
How long is it going to be the test?
Do you mean how long does a test take to do it?
No, like how many questions?
Close to 100.
Okay.
It's pretty intense actually. And I think that's next week, so we ought to do some training before. Actually, I'm sorry, it's 2 weeks from now, right? Because next week we have a missing Monday, isn't that right?
Yeah.
There's a holiday next Monday. I
Yeah.
figured on Wednesday we'll do some training for the test, okay, Juan?
Okay. Because I need it.
Yes, we're all going to need that, and that's going to be very helpful. Okay.
Thanks.
So, but I just want to get you guys thinking, so you can write down into your notes, hey, this is going to be on the test. This is important. Okay. You'll know when you're studying. When is the test, Ava? The test is whenever it says on our syllabus. I think it's 2 weeks from today, but let's check. Here's the 1010 schedule, which is right in your Blackboard. Today is October 5th. So next week, we don't have class on Monday. On Wednesday, we'll have a lecture plus a training session. And then Monday, October 19th is the test, Ava. Okay? All right. So Newton's version of Kepler's third law is a really important formula in astronomy. That's why I'm taking a lot of time talking about it. I'm tempted to do a sample problem on it right now, but the reality is that we're going to be doing a sample problem during our lab today on this formula. So I think I'm just going to hold off till then so I can cover some other ground. Is everyone okay with that? Remember, you did practice this during your homework session last week. All right. Do you guys remember what Newton's version of Kepler's second law is, or could you look it up in your notes if you cannot remember?
I got you.
Thank you.
What is it? The second law?
Yeah, the Newtonian version of Kepler's second law.
So the definition of force equals mass
sorry.
times acceleration.
So these are going to get all mixed up. That's Newton's second law, but I'm asking you about Newton's version of Kepler's second law. Not exactly the same thing.
All right.
Newton's version is
I found that. Oh wait. Try on the next page. Is it gravitational law?
Nope, that's a different law.
Is it equal areas and equal times?
Yeah, it's the same as Kepler's version. It's the law of equal areas,
Equal.
which is the same thing as, yeah, equal areas and equal times. Let's look at the cartoon picture in case anyone missed that the first time around. That does seem to happen. Here we go. So a planet will sweep out equal units of area and equal units of time. Basically, it tells us that the planet travels faster when it's closest to the sun. It travels slower when it's farthest from the sun. Now, last time I hinted at the fact that Newton discovered that equal areas and equal times was true, and that it didn't need to be modified like the first and the third law. But he discovered that there was a reason for it, The reason was something called the conservation of angular momentum. And that's a concept that comes up from time to time in astronomy. So it's something that I wanted us to discuss. Unfortunately, you can't really discuss angular momentum until you start off by learning about linear momentum. Angular momentum and linear momentum are two different aspects of momentum. In fact, maybe some of you out there have taken a physics course and you already know what this is. Any chance that's true? Well, in any case, when we talk about linear momentum in physics, we assign it the letter P for random historical reasons. And you might think of linear momentum as the amount of oomph of a moving object. Momentum is kind of a difficult thing to talk about, but you could think of it as the amount of oomph of a moving object, if you know what I'm saying. It has a definition: the product of an object's mass times its velocity. You know, it's a great, well, I'll show you a demo in a second here. Linear momentum, the amount of oomph of a moving object. And in physics, linear momentum is important because it's what we call a conserved quantity. A conserved quantity means the total momentum in a closed system must remain constant. And that doesn't sound like much when you first hear it said, but the fact is, if the total momentum in a closed system is constant, if it's conserved, you can actually analyze the dynamics of a situation, and you can predict what will happen when two things collide with each other. This could benefit you if you like to play pool at the bar at night, or if you want to analyze particle collisions in the Large Hadron Collider. Maybe one of the funnest demonstrations of linear momentum is this fun office toy here called Newton's Cradle, right? I bet you guys have seen this before. You have a bunch of metal spheres suspended off of thin fishing wires, okay? And because the spheres are equal in mass, when they undergo a collision, momentum gets transferred as if by a magical fluid through the little spheres to the one at the end, right? So you can sort of lift this one back and drop it. You can watch the momentum of your moving object get transferred back and forth. You can even do fun variations in this where you, it would be nice if I could, I didn't think this demo through as carefully as I should have. Where could I need a box. Yeah. This may hit a button on our computer, so I'll have to be careful here. Okay. You can even do fun versions where you pull two back. Or you can even do this one. This one's always kind of cool. In any case, using the equations of momentum, you can predict all of those collisions. You can predict what will happen when two objects bump into each other. And there's kind of three classic scenarios that come to terms with linear momentum. If you have a situation like the one that you just saw there, where there are two particles of equal mass, if one has momentum and it crashes into the other, if the particles have exactly equal masses, usually the first object comes completely to a halt and transfers all of its momentum into the second object. So this is why a game of pool works the way it does, because when you have your cue ball, usually your cue ball is close to the same mass as your 8-ball, and when it hits that particle, it stops and the other thing begins to move. The other two scenarios that come up from time to time are the scenario where you have like a bowling ball and a BB, right? If you fire a BB at a bowling ball, it will bounce off the bowling ball and ricochet back. The momentum is kept in the little particle. if the bowling ball hits the BB, usually the bowling ball will scoop up the BB and snowplow it along and carry it with it. So those are the three examples of collisions. When you have equal mass particles, one stops, the other moves. And if they're lopsided, you either have a ricochet or a snowplow. And when it's somewhere in between those scenarios, you have to analyze it specifically. You know, like if you have one that's slightly more massive than the other, then different things happen. Now, I don't have time to teach you physics 1, but you do want to be roughly aware that there's this concept called momentum. It's an abstract quantity, and it tells you something about the oomph that a moving object carries with it. It's not just its speed, but it's also its mass. Now, every time we have a cool quantity like linear momentum or force in physics, there's a variation of it that shows up when you start to rotate a system. Rotations are complicated, and rotations introduce different types of forces and coordinate systems that you have to take care to analyze in physics. So there's a concept called linear momentum, which involves a particle traveling in a straight line, and there's a related concept called angular momentum. So introducing angular momentum. For some reason, historically, angular momentum is given the symbol capital L. And angular momentum tells us something about rotating objects, okay? So let me just show you a cartoon picture of your sort of most basic, simple setup for angular momentum. I have it in the slideshow, but I have to I have to look around for it here. There we go. So here in the most basic setup, you have a particle with mass m, some kind of BB. It's traveling at a velocity v, but instead of just traveling straight through space, it's rotating on a circle. Here it's constrained to move on some kind of a wire or a thumbtack that's been tapped down to the page there. And so the particle is just kind of swinging around in a circular orbit. When this happens, we can define the angular momentum of the particle as its mass times the velocity times the radius of orbit r. Let's write that down on the board. Angular momentum is a slightly different beast than linear momentum. But like linear momentum, angular momentum is a conserved quantity. Because it's a conserved quantity, you get Nostradamus-like powers, and you can predict what will happen when the system changes. One of the concepts behind angular momentum goes something like this. Objects that spin want to stay spinning and in the same direction. It turns out that you can assign a direction to angular momentum, but it's not the direction that you might think. If you look at the particle traveling on the circle here, you'll realize that its direction is constantly changing. In that one moment, the direction of velocity is here towards the blue arrow, but a moment later, the direction will be there. A moment later, the direction will be there. And the direction is actually constantly changing of the particle itself. But what you can do is, if you're clever, is you'll realize that there is something that is not changing here, and that's the axis of rotation. So we actually define the direction of angular momentum as being along the axis of rotation. And that has some kind of goofy consequences that aren't really obvious to predict. Let's see why the conservation of angular momentum can get weird sometimes. I have in my hands here a bicycle wheel, okay? And the bicycle wheel has mass you know, along the rim of the tire. I can hold it by this string here. And when it's not spinning, if I let the wheel go, gravity just kind of pulls it over and flops it in any old direction it wants. But something cool happens when I give the wheel some angular momentum. So I'm going to get this bad boy spinning. And now I can hold it by the string, and gravity is unable to pull over the wheel, right? Even if I give it a whack, watch this. I'm going to try to knock this thing over. I can't do it. It won't let me. By the way, this motion here takes a little bit of understanding to figure out what's going on. This is called precession. Precession happens with the Earth and other planets, and all of the planets in our solar system are sort of driven by angular momentum. This is why you don't fall off your bicycle when it's moving, but you do when it's stopped. You are literally being held up by angular momentum. Angular momentum is the principle that makes gyroscopes work. It's why those guys who are now skating around the park on those little one wheels, have you seen the one wheels? Because I see them all over Providence now. Those guys can just go flying on a single wheel, and they can stay balanced because the angular momentum of the wheel actually stabilizes their motion. We use gyroscopes in space telescope design. By spinning up and spinning down a wheel, you can actually cause telescopes to move in space as they attempt to conserve angular momentum. Angular momentum just has a lot of funky effects that you wouldn't necessarily predict beforehand. In a physics 1 class, you would probably do a more complete analysis of what just happened there with the wheel. I don't know if I have time to get into all that craziness, but I think you should be aware that there is a concept called the conservation of angular momentum. Let's take a look at how it would affect Kepler's second law of planetary motion, right? Now, as a planet orbits the sun, the mass of the planet is not allowed to change unless, I don't know, maybe you broke off a big piece of it in an asteroid collision or something. Usually planets keep a conserved mass. So what's happening is when the planet comes in close to the sun, this distance here, which is its radius of orbit, begins to shrink. And if the radius of orbit begins to shrink, the only way to conserve angular momentum is for the particle to speed up and go faster. Likewise, when the planet or the comet is way out here, its radius of orbit has increased, and therefore its velocity is smaller now to conserve angular momentum. This is why a comet like Halley's Comet, which has a very eccentric orbit, might spend 76 years, or almost 76 years, out near the orbit of Neptune, and then only a few months in close to the sun, because there's a really big change in the radius of orbit. There's also a big change in the speed of the comet as well. Okay, these are little concepts that I wanted to kind of just throw in your toolbox there. So make sure you get this note down before I move on. How do you guys feel about me erasing this? Is that okay? All right.
I'm still writing.
Oh, okay, sure. Take a moment. Let me know when you're done.
I'm done.
Okay, cool. Okay, so as I warned you guys today, you're going to learn a whole bunch of little different pieces of physics. One that we did a problem on that I need to kind of introduce formally to the class is the concept of escape velocity. And escape velocity gets the symbol in this class, V subscript escape. Escape velocity is another concept that came out of Newton's analysis of motion. Escape velocity is that unique speed that any object needs to escape a planet of mass m and radius r. And our setup goes something like this. We've got a planet. The planet has some radius and some mass, which are usually given to you. And then you want to try to find the speed that a rocket would need to blast off of that planet. There is a way to think about it conceptually. If you look at one of these crappy diagrams with me, I may be able to explain escape velocity a little bit better. As you guys know, Newton developed 3 laws of motion, which would tell people how particles move when subjected to forces. And one of the things we discovered is that you guys might know this just from kind of living life or playing sports. Let me share screen and go to your whiteboard. If you throw a ball through the air, the motion that the ball travels on is usually a parabola. It kind of goes up on an arc, reaches some maximum height, and then it comes down and falls to the ground. If you know the force or the speed or some aspect of how the ball was thrown, you can usually calculate how far the ball will travel and how long the ball will travel before it comes back down and strikes the ground. That's a kind of classic physics problem. Now, when Newton analyzed this, he discovered that if you consider the entire curvature of the Earth, let me get this down at the bottom here. When you do something like fire a cannonball out of a cannon, it also travels on a parabola, just like a baseball or a basketball. And at some point, it will sort of fall down to the ground and it'll travel some maximum distance or range. If you fire it faster, the range will increase, and the range will increase more if you fire it faster. On Earth, particles like cannonballs and bullets have to contend with air friction, which tend to slow them down and add drag and pull them to the ground. But what if you tried firing a bullet on the surface of the moon? On the surface of the moon, there is no air to slow down the motion of your bullet. So if you fired a bullet fast enough, you could actually get it to miss the curvature of the moon and actually travel all the way around the moon in a low Earth or a low moon orbit. And then you could actually shoot yourself in the back of the head if you were clumsy enough to do this, right? So without the presence of air to slow down the bullet, if you fire it at this one critical speed, you could actually miss the curvature of the planet and you can go into a kind of low Earth orbit. And that's the idea behind escape velocity. It's that critical speed you need to miss the curvature of a planet. I think we should try an example by calculating the escape velocity of Earth. So let's do an in-class example. This will be a useful reference for us. Yes, Kelly, it would stay in orbit. The bullet would orbit just like a satellite. In a way, Kelly, that's what we do when we fire like a space shuttle or a satellite into space. We're doing just that, except with a bigger payload. I don't believe I know of any guns that can achieve escape velocity, but at this point, we have to use rockets to do it. So let's try an example, and I'll say more about that in a second, Kelly. Let's find the escape velocity of Earth. Oh, I guess I have to give you the formula, don't I? The escape velocity, the escape, is the square root of 2 times g times the mass of the planet divided by the radius of the planet, okay? And here, all units should be in MKS units. So the mass should be in kilograms. The radius should be in meters. So let's try a problem where we find the escape velocity of Earth. I'll have to give you the mass and the radius, and I have no problems doing that. The mass of Earth is 6 times 10 to the 24 kilograms. I'll use blue for my units. The radius of Earth is 400 kilometers. What do you guys think I should do to start this day off here? Or to start this problem off?
So we need to convert
Conversion.
4,600 kilometers to meters.
That's right. And Ava noticed that as well, Frank. That's really good. So Frank, I guess that's a you job then, isn't it?
Mm-hmm.
Are you willing to do that? How do I do that?
Yeah. You need, obviously, you need dimensional analysis.
Yes.
Uh,
So we'll put it in division.
it would be. Mhm. It would be meters on top and kilometers on bottom.
Correct. And now we need a conversion factor.
That would be 1,000 meters to 1 kilometer.
Damn, you're good. I like it. Can you do that one up in your head, Frank?
Yeah, just. Yeah, I got 6.4 times 10 to the 6th.
Very good. Because you can see, Frank, you've got 1, 2, 3 zeros, right?
Mm-hmm.
4, 5, and then the 4 is a 6th zero. So then the radius of Earth becomes 6.4 million meters. Sorry, I had to put it over on the left side here because I ran out of space. Okay, now everything's in MKS units, so we should be good to go. Right, Frank? Guys, just take a moment to, yes, Haven, now we can follow the formula. Thank you much. But can you guys finish writing this? Because I'm going to have to erase. I ran out of space here. Maybe I can erase up here at the top. Okay, so we're going to calculate the escape velocity now. So let's set up the equation just like Ava suggested. Make a nice big neat square root that will keep everything inside of it. Okay, so we have 2 times big G, which is about 7 times 10 to the minus 11. Big G has crazy units, meters cubed per kilogram per second squared, times the mass of Earth, 6 times 10 to the 24 kilograms. Man, my handwriting sucks today. 6 times 10 to the 24 kilograms divided by Frank's 6.4 million meters. Okay, guys, punch it up. Take out your calc keys and see if you can handle that. Anyone got something for me? Someone's rocking out back there. I just want to see if you guys can handle this.
I
What you
got 1.3 times 10 to the 8.
You forgot to square root it. Matt, you did something wrong, Matt. Too big. Anyone else? So far, no one's gotten the right answer. Yes, Frank. Frank's got it. Bella's got it. Rory's got it. Sorry,
I'm
Yin.
confused with
Small.
this division part.
Okay. Do we want to do this as a class? It looks like enough people got it wrong. We're Matt, that's good. Yes, okay. All right. Yes, Noah. So let's punch together. First, we'll do the inside of the square root, okay? Sorry, I've got some glare on this thing. I'm trying to figure out how to fix it. All right. So we'll do 2 times 7 exp negative key 11 times 6 exp 24, that's the mass of the Earth, divided by 6.4 exp6, that's the radius of Earth. Then we hit equals, and then we shift and square root it. Okay, so how should we round this number, guys? How should we round the number?
$11,000.
That sounds good to me.
Dude,
I like
meters squared
11,000. What about the units?
Meters squared per second squared.
Who said that?
No.
Noah, you are almost right. Noah sees that meters cancel with 1 meters to make meters squared and kilograms cancel. But Noah, it ends up being the square root of meters squared per second squared. And you have to
so just
distribute the square root, right? So what are your
meters per
final
second.
units?
Meters per second.
Very good. Hey, Noah, while you're at it, can you tell me how many kilometers per second that is?
11.
That's very good. If you divide that by 1,000, so meters to kilometers is 1 to 1,000. You end up with, and by the way, even though our answer came out in meters per second, Noah, it's just customary to express escape velocities in kilometers per second. That's like a classy thing to do. So 11 kilometers per second is the escape velocity of Earth. Is that fast, class? Do you think 11 kilometers per second is fast? Yeah, it's probably really fast. Let's do something here together. Let's share screen. Let's do a Google conversion real quick. 11 kilometers per second to miles per hour. That's about 25,000 miles per hour. By the way, that speed, it doesn't depend upon the object that you're trying to get off of the Earth. If I could take this dry erase marker and I could just give it a huck at 25,000 miles per hour, I could actually shoot this thing right into space and jump off of the gravity of Earth. Same for a marker as it is for a dump truck or a rocket ship. 25,000 miles an hour, you hit the ramp, you're out, okay? One of the things that's difficult about rocket science, however, is, you know, the way you get a rocket into outer space is it starts from rest. It's not moving. And you have to fill up the rocket tank with a solid oxygen fuel, which provides thrust and thrusts you off into space. Even though the escape velocity might not depend upon the rocket, the thrust does depend upon how massive the rocket is. And if you think about how Newton's second law of motion works, because force is equal to mass times acceleration, you have to accelerate the rocket to go from 0 meters per second up to 11 kilometers per second. And the acceleration is equal to the force divided by the mass. The force is the thrust of the rocket, and the mass is the mass of the rocket. But here's the problem. Fuel is heavy. So what happens is you take your rocket and you start by putting some oxygen fuel into the tank so that you can provide this thrust. But the oxygen fuel has mass, and that adds to the mass of your rocket. And that means you have to put even more fuel into the rocket to try to get even more thrust to account for the mass. So you keep dumping more and more fuel in, and at the limit of our current rocket technology, the whole problem kind of tapers off somewhere around 10 kilometers per second, and that's about the maximum thrust we can get our rockets. Right, Matt? So in other words, we should not be able to go to outer space. And yet, here's the trick. The secret to getting to outer space is that on a rotating Earth, we have a non-zero velocity through space. So if you're standing up here at the North Pole, during 24 hours, you kind of do this. Okay, that's not really a velocity through space. You're just spinning. But as you go down further and further south in latitude, you're actually spinning through a bigger and bigger circle in 24 hours. So your velocity through space increases all the way down to the equator, where you travel like 40,000 kilometers per day. It turns out that somewhere around a latitude of 30 degrees, which is where we have Cape Canaveral, Florida, your velocity through space is just about 1 kilometer per second. So what you do to get into space is you fire your rocket up at 10 kilometers per second, and you fire it into the direction of Earth's rotation, and the rotation of Earth gives you the last click per second that you need to get up there into outer space. And for this reason, when you guys watch rockets being launched from Earth, so let's just look at a shuttle launch. You'll notice that after, let's just see if we can go to images and get a cool high resolution image. After they fire the shuttle off into space, you'll notice the shuttles kind of curve or take a sort of left-hand turn over the Atlantic Ocean. Sorry, my internet's acting sucky today. Wow. Yeah. So I guess that they call it the tilt shift. There's a kind of cool yeah, okay. So here's this rocket launch. You can sort of see, can you see how it's taking this curved path here? It's taking a while for this photo to come into resolution here. My internet must be lagging because of my video sharing. There we go. Open image, new tab. So you can see that after they launch this shuttle launch, you can see it's already making a curved trajectory. If you continue to watch the thing, it really curves hard into the direction of Earth as, oh, I like this one here. This one's nice because it shows you it from like an F-15 or something. It's kind of cool. So here you can see, this is like just a really cool picture from the internet of these two F-15 jets. You know, you're inside one of the cockpits there, and you're watching the thing blast off, and you can see it curving and spinning into the Earth's direction. So to actually fly to outer space, you kind of have to be very brave, because you're using the rotation of Earth to give you that last little bit of lift that you need to get out into outer space. The reason why I'm teaching you the escape velocity is not so much because this is a class on rocket science, but because the escape velocity ends up being a number that gives you a rough sense of what the gravity of a planet is like. For instance, Earth's escape velocity might be 11 kilometers per second, but Mars's escape velocity is only 5 kilometers per second. So if we do send humans to Mars to set up a colony there, the good news is if we decide that we get sick of Mars and we want to come home, it's easier to escape the surface of Mars than it is Earth. The bad news is there's no Cape Canaveral on Mars. So you're going to have to set all that stuff up yourself, and that might not be an easy job. Okay. Another module completed. Class, can I erase this? All right. All right. Last time we spent a little bit of time learning about Newton's law of gravity, and we calculated the force between Earth and the moon. we also calculated the force between Earth and the sun. And what did we discover was stronger, the Earth-Moon gravity or the Earth-Sun gravity? Why don't you guys look that up?
The sun gravity.
Right. We found if we plugged in the mass of the sun and the mass of Earth and the distance between them of 1 AU, the force of gravity of the sun and the Earth was 400 times greater, 200 times greater than the Earth-Moon gravity. And yet, you've probably been told at some point in your life that it is the moon that it is the cause of tides, not the sun. And that's a little bit weird to understand because, shoot, I keep losing my slideshow here. Bear with me for just a moment. I don't think we actually covered tides very well last time, so I want to make sure I do that this time. So can you guys think of a reason why it would be the moon causing tides and not the sun? Considering the fact that the moon is closer, but also less massive than the sun, why would the moon be the cause of tides if its gravity was 200 times weaker than the sun's? Okay, well, I guess I didn't expect you to have an answer for that.
Can I
thought it would-
speculate? I don't know if it's the right answer or not. I'm just guessing.
Yeah, sure. Speculate.
Is it because the gravitational field is smaller between the moon and the Earth as opposed to the sun?
Well, gravitational fields affect the force of gravity. A smaller gravitational field means a stronger gravitational force. My conundrum that I want you guys to think about, or the trick that I'm playing on you, is why does a smaller force give a greater tidal force? It's messy. It's not as easy to explain as the law of gravity is. So let's take some notes and I can help you understand that riddle, okay? Let's talk about, instead of the law of gravity, let's talk about the tidal force. Tidal forces actually play a huge role in astronomy at all these different levels. So we could say this. Tides are caused by gravity, but the tidal force, as we call it, is not the same as the gravitational force. So the tidal force does not equal the gravitational force. There's actually different formulas that describe the two. The tidal force is here's the fancy term here. It's a differential force, okay? A differential force that acts over an extended body, such as the Earth. Yet another way to say this is that the tidal force is a delta force, a change in force between the difference of the force acting on the front of a body minus the force acting on the back of a body. It's a change in force from the front side to the back side of an object. And because the tidal force is ultimately, I'm going to use a fancy term here, the derivative of force, the tidal force is proportional to the cube, inversely proportional to the cube of the distance, not the square of the distance. And that's a little bit crazy. That means that tidal forces get weaker with distance faster than gravity does, but they get stronger faster than gravity when you get closer. My D looks funny, so I'm going to fix it. Okay, let's see if I can draw this in cartoon form so that you guys can understand this, okay? I'm going to use my whiteboard here and see if this gives me any benefit. Suppose I were to draw the Earth and the Moon, okay? So let's use blue for the Earth. So here's the Earth, and I'll just use black for the Moon. Here's the Moon. And the Earth and Moon are separated by each other by a distance of, I think, 384,000 kilometers. So let's do our text. I wish the text was smaller. 384. But as you guys just learned, the radius of Earth is 6,400 kilometers. So let's do some quick math together. What is the diameter of Earth, front to back?
12,800.
Good. And now what I want to know is what percentage of this distance is the diameter of Earth? So if I just asked you guys a simple question, and I want to know what percentage of the distance between Earth and the Moon. So to get a percentage, you have to do 12,800, right? Divided by 384,000. Why don't you guys do that? Because I can't really spell very well with this marker. What does that give you? Could you punch it for me?
0.03333, repeating.
We'll just leave it like that. What is that as a percentage, Rory, if that was your voice that I just heard? Or I don't know who that was, but.
It wasn't, but it's 3%.
3%, right? So as you guys might know, that's the same as 3%. Okay. Now here's what I need you guys to do. Let's imagine that I could take a planetary-sized cheese grater, and I could slice Earth up into these very thin wedges of cheese, okay? So I'm going to slice a little slice of Earth cheese up near the front of the planet, and I'm going to slice an identically thin slice of Earth cheese near the back. Let's just undo those last two. Let's see if I can make them a little closer to each other. So this one, here's a thin slice in the front, and here's a thin slice in the back. Each of these thin slices of planetary cheese should have a mass associated with them. How will the force be different if you're on the front slice versus the back slice? Well, the front slice should feel one force of gravity, right? And that should be the force on the front side. And then there should be a force on the back side, and they'll be different from each other. If I slice them thin enough, I guess I could make the force on the front side be, I don't know, 40 newtons. And maybe the slice on the back side, which is 3% farther away, it would have a different force, like 20 newtons. I'm just making up some numbers here for fun. And that means the tidal force acting on Earth, the delta force, would be 40 newtons minus 20 newtons equals 20 newtons. And that would mean that Earth was experiencing a side-to-side shear force, a pulling apart force of 20 newtons across its body. And let's think about what that would do to the Earth. From the Earth's perspective, that difference in force between the force on the front and the backside is going to create a pulling apart force that results in two high tides, a high tide that's in the direction of the moon and a high tide that's opposite the moon. And that's because the Earth is being pulled side to side like a teddy bear being pulled apart by two kids who are fighting over it, okay? It also creates low tides perpendicular to the moon as the gravity pulls the oceans down towards the rock. Another way to think about that, about the second high tide, is you could imagine that the center of Earth is getting tugged stronger than the backside. So you're actually tugging Earth away from the water. Not only does Earth experience 2 high tides per day in terms of water, but remember that the Earth is surrounded by a fluid of atmosphere, and the atmosphere also bulges in the direction of the moon. And what's even crazier is the rock underneath your feet. The rock of Earth actually bulges towards the moon by about 2 or 3 centimeters per day. And that means you're actually deforming the Earth from a spherical shape into a slightly football shape, and it bulges towards the moon. So the ground rock underneath your feet gets lifted up by just a couple of centimeters each day in the direction of the moon. We call those rock tides. Obviously, they're much less than ocean tides. Now, suppose, hypothetically speaking, suppose you were a pesky student and you wanted to ask me some pesky questions. You might say to me, okay, Brendan, you've said that the moon is exerting this gravitational tidal force on the Earth, but isn't the sun's gravity 400 times greater? Why doesn't the sun exert these forces? To answer that question, we're going to have to think about the difference in Earth's body versus 1AU, okay? So here is Earth, and here's the moon. And you guys know that the diameter of Earth is about 3% of this distance, right? What if we considered the sun? The sun is located 1 AU, or 150 million kilometers away. The Earth has a diameter of 12,800 kilometers. Let's figure out what percentage of 1 AU the diameter of Earth comprises. So I've got 12,800 kilometers divided by 150 million kilometers. Why don't you guys punch that up for me? Okay, how do I say that, Noah? Round to 1 sig fig for me.
Like in scientific notation, or
Sure, we'll start there.
it would be like 8.5 times
That's 2 sig figs, Noah.
2 sig figs.
I want 1.
Oh, so 9 times 10 to the negative 5.
Okay, could you help me write that number out for the benefit of the class? Just in case anyone out there still sucks at scientific notation, we should probably write this out longhand.
You're gonna have 4 zeros after the decimal point.
Good. The 9 is the 5th zero, right? What would that be as a percentage, Noah?
2 zeros behind the, I guess, 1,000th of a percent, or
Oh, good. Or
9 thousandths.
9 thousandths of a percent, right?
Yeah.
That's 9 thousandths of a percent, which is close to 100th of a percent, right? Okay. In other words, the change in distance between the front and the back of Earth is a lot smaller percentage-wise compared to 1 AU. So maybe the front side of Earth gets tugged on by like 400 newtons, but the back side of Earth would only get tugged on by say 399 newtons, because the differential force across its body changes by less. So the tidal force due to the sun would be 400 minus 399, or only a 1 Newton differential. Therefore, it is possible to say two things that sound contradictory, but are actually not. The gravitational force that the sun exerts on Earth is at all points on Earth greater than the gravitational force the moon exerts on Earth. Yet the differential force, the tidal force that the moon exerts, is greater than the tidal force that the sun exerts on Earth. For that reason, it is the moon that dominates tides. Although you should be aware that the sun does actually affect tides. As any good cawhogger out there would know, there are tides twice a month called spring tides. These are unusually strong tides. And that happens during new moon and full moon. When the sun and the moon are in alignment, their gravity adds together, creating especially high tides that day. There are also neap tides, which occur at first and third quarter, where the gravity of the sun offsets the gravity of the moon, and that makes slightly weaker than average tides. So spring tides and neap tides are a cool example of tidal forces interacting between the moon and the sun, okay? Tidal forces affect planets and moons all throughout our solar system in complex ways. You guys might not realize this, but there's a critical distance at some point when moons get a little too close. Now, moons occasionally do gravitate and drift inwards and outwards, partially due to the conservation of angular momentum. The fact that Earth bulges like a football in the direction of the moon causes the Earth to undergo torques from the moon, which are slowing down the rate at which Earth spins over time. In the case of our Earth-Moon system, Earth is losing like a second every century, something crazy like that. And the length of a day is slowly increasing. And as Earth slows its spin, in order to conserve angular momentum, the moon actually drifts slightly farther away from the Earth by like a centimeter each day, because the loss of angular momentum of the Earth has to be compensated for by a gain in angular momentum by the moon. It's kind of wild how that works. And those kind of driftings towards and away from planets happen all throughout our solar system. Maybe one of the most dramatic examples of tidal forces has to do with one of Mars's moons called Phobos. Actually, I think it's not Phobos, but Deimos. Well, I'll show you a picture of Phobos because I don't have a good picture of Deimos. Here's one of Mars's natural satellites. It kind of looks like a big old captured asteroid. It's called Phobos. Phobos is really small. It's maybe 12 or 13 kilometers across. So it's a very small like asteroid. There's another moon called Deimos, which is orbiting Mars. And Deimos has actually drifted towards Mars and has gotten so close that the magnitude of tidal forces on Deimos, the difference between the front and the back pull, have actually started to grow to the same size as the self-cohesive gravitational forces that bind the moon together. So we believe that at some point the moon Deimos is going to undergo a tidal disruption where tides pull the moon apart into a disk of debris, and then the moon will basically be ripped apart into a rocky ring system. And if you were to go like a million years from now, Mars is going to have a little ring of dust around it where the moon that was once there just got pulled apart. That also helps us to understand about how some of Saturn's rings have formed. Saturn has these big, beautiful icy rings, but it's also surrounded by little icy moons. And at some point you start to realize, oh, those moons are drifting in towards Saturn, and Saturn is just chewing them to pieces and adding to the ring system. So tidal forces affect all of these cool features in our solar system, right down to the rings of Saturn. They're cool to know about. Okay, how am I doing on time here? I want to make a transition away from concepts like Newton's laws and towards concepts like energy and light, which are going to be the business of this week's lecture. I think I'm still in full screen mode here. Okay. Oh gosh, 12:51. Actually, it looks like I've kind of busted myself and used all the time I have for today. I think we're going to stop there. How do you guys feel? Would we like to do a little 10-minute break or so before we get going on our lab? Everyone likes that,
Yes.
right? Okay.
What
Yeah.
time does class end today?
Absolutely.
Well, if we get our lab started a little bit after 1, I think we'll definitely finish before 2 because this is a shorter than average lab.
All right. All right.
Does that help?
Do we need
Yeah.
clean paper for our lab, or is there an actual lab that we need to print out?
This is one of the few labs where there's no like printout needed. We're basically just going to do a math problem that's almost identical to the test. And my logic is this. I know a lot of you guys are going to struggle with NK3, and I know it's going to be on the test. So why don't I help you by doing a lab where we kind of work out a sample problem? This will have a 2-for-1 benefit of being, we're doing a lab, but we're also slowing time down and practicing for the test. So all you need is a calculator, a pencil, and some notebook paper, okay?
Okay.
And
thanks.
I'll walk you through the whole damn thing. Okay, so let's take a 10-minute pause, maybe 15 if I'm feeling crazy. Okay, but a little bit after 1, we'll get started. Okay, welcome back, Astronomy 1010. Our goal today is to calculate the period of the International Space Station. So let's just start by showing you guys a picture of the so-called ISS. It's a collaboration between NASA and the European Space Agency and many other science organizations around the world. It's basically a space station that's manned continuously by astronauts and cosmonauts. They live up there year-round performing experiments in microgravity. They do physics research, astronomy research, all kinds of interest, even biology research. It's cool because you can actually see the International Space Station with your naked eye if you know roughly when and where to look. When you see the ISS fly overhead, it looks like a very bright star, usually almost as bright as a planet or sometimes even brighter. And it moves on a polar orbit. So it's usually either traveling from north to south or sometimes from south to north. And it's very, very bright. You can tell that it's much higher
How
than.
did they get that thing up there?
Well, piece
That's
by
my
piece,
question.
they had rocket launches where they took module after module up to it, and they're constantly building it and improving it. The Japanese module is one of the more recent additions to the space station. So Andrew, they just take things up piece by piece and assemble them up there in outer space. Our idea is this is the perfect opportunity for us to kind of test out Newton's version of Kepler's third law, because Kepler's third law wouldn't be able to calculate the period of the International Space Station. That's because it's not orbiting the sun, it's orbiting Earth. But this is a perfect job for the for NK3. So let's see if I can share my phone here with any success. I'm going to share to the phone. Excuse me. There we go. Looks like it's working today. And you guys can see I've got some paper here and a calculator. Let me adjust the lighting so that it doesn't. Actually, I should take off the lock. And I also need to go to settings to go to my display. And I want to turn off my auto lock. Okay. Okay. So let's see if I can turn this thing sideways. I've got a nice piece of paper to work with here. It might be nice to have a ruler if you have one of those handy. I might even use a compass so I can make a nice perfect circle. Circle makers are also good for this tool. So let's start up at the top here, and we'll have our names. Oh, sorry. That's sideways. There we go. Okay. So we have our name. We'll put down astronomy 1010 and our section, whatever your section is. And then this is LAB5, which is the period of the ISS. So you guys can get all of that down if you're willing to. Let me see if I can reduce the light a little bit. Okay, there we go. Okay, so let's take a look at our givens. We're going to draw a cartoon of what's going on here. So let's draw a representation of planet Earth. I'm going to make this about, oh, I don't know, maybe 3 centimeters or so. Okay, so here's Earth, and I'm going to draw in Earth's radius, which we're going to need to solve this problem. There's the center of Earth. There's the radius of Earth. And the International Space Station is orbiting, I don't know, about 400 kilometers above the surface of Earth. So what I'll do is I'll kind of draw a simplified version of the ISS, kind of look like a piece of candy or something with, oh, sorry. Are you guys seeing this?
I think it froze.
What? How did that happen? Sorry, guys. I think I hit a button or something. Oh no, it's doing the thing again.
Uh-oh.
Usually if it works the first time, it won't work the second time. Or maybe I'm just crazy in imagining that. Oh, there we go. It says it's connecting. Come on. Wait. Actually, it says Apple TV. No, Zoom be Britain. That's right. Wow, I've totally messed this up, guys. I'm so sorry. Hold on. Try again. It's giving me the waiting symbol here. Sometimes if I just wait a minute, it will work. I'm going to pause this recording until I figure this out so I don't waste everyone's time later on. The height of the shuttle is 400 kilometers. Let me see if I can get this share working again. There we go. Okay, we're back. Sorry. So you guys will see that I've drawn in the height of the shuttle is 400 kilometers. I'll need to give you the radius of Earth, which I gave you in today's lecture, is 6,400 kilometers. The mass of the Earth is 6 times 10 to the 24 kilograms. And the mass of the ISS is 400,000 kilograms. Okay. Let me sharpen my pencil here. All right, let's write down Newton's version of Kepler's third law. So we have p squared equals division bar 4 times pi squared times a cubed divided by g times the sum of the mass of Earth plus the mass of the ISS in parentheses. My division bar got kind of bad there, so I'm gonna, oh, fudge an A. All right, let's see if we can identify all of our variables. Sorry, that looks like hell. We know 4, we know pi squared, we know big G. Big G is always 7 times 10 to the minus 11 meters cubed per kilogram per second squared. We need to focus on the A, we need to focus on the mass. Let's start with the A. What is the A here, students? What are we
400
using?
kilometers.
You would think so. Except, Joel, remember that the shuttle is not orbiting around the surface of Earth. The shuttle is orbiting the center of Earth.
6,800.
That's right. This is a trick, and you've got to remember this trick. A is the center to center distance between the two orbiting bodies. In a situation like this, the radius of Earth is actually greater than the separation between Earth and the shuttle. So RA is the height of the shuttle plus the radius of Earth, 400 kilometers plus 6,400 kilometers is 6,800 kilometers. That's the A. What units does A require in this formula?
Meters.
So we'll have to deal with that, right?
Yep.
Okay. Joel, I guess you're talking with me. You want to help me work that out?
I wonder if Andrew remembers.
Huh? You wonder if Andrew remembers? Come on, you can do this, Joel. I'll set up your division bar.
6.8 million meters. But
Very good.
it's meters over kilometers and 1,000 over 1.
Okay, cool. So keep in mind, guys, Joel is pretty good at this, so he may not have been the best person to choose. I want to make sure that you guys are all good at your dimensional analysis because you're going to have to do it all the time to get these problems right.
Well, at least this time I remember to do dimensional analysis for you, unlike usual. I just give you the answer.
Well, that's what the test is. The test you guys are going to have to remember. You're going to have to remember to do this stuff, right? All right, let's focus. Let's talk to Jake here. Jake, we're going to need your help.
I'll see what I can do.
Okay. We're going to need to focus on this for a second. I want to calculate the total mass of the system. The total mass of the system is the mass of the Earth plus the mass of the ISS. 6 times 10 to the 24 kilograms plus 400,000 kilograms. Can you add those two up with your calculator, Jake?
Yeah.
And by the way, when I say Jake, I really mean all of you. I'm gonna break this desk one day. Okay, what do you get?
Well, I got 6 to the 25th, but I don't know if that's right.
6 to the 25th, definitely. Did you use the plus sign, buddy?
I absolutely did.
What's this? Sorry, Jake, you kind of glitched out there.
Oh, sorry. What?
Could you do it again, buddy? Could you add them
Yeah,
up?
yeah.
You screwed up somehow.
So instead of the addition, you do multiplication, right?
No, you do addition. That's why I used the plus sign.
You do? Okay.
Yeah, it's the sum of the masses, not the
Okay.
product of the masses.
To the 24th.
I got
What's that?
6 to the 24.
No, wait a
I
minute.
got
That's
6 to the 24th.
That's what I
the
got.
mass of Earth. You've got to add the mass of the ISS to it.
So is this one of those situations where the mass of Earth is so large compared to the other that it's irrelevant?
That's right. Who got that? Who knew that?
Rory.
Yeah.
Rory, that's right. Rory, I didn't know how else to, sometimes you try things one way, which is just telling people what's up, and people just tend to not listen to you because that's the way they are. So this way I was trying to trick you guys, but Rory figured out my trick. He knows that I'm trying to trick you guys, okay? So obviously the mass of the ISS is tiny in comparison to the mass of the Earth. So the total mass of the system is basically just the mass of the Earth. 6 times 10 to the 24 kilograms. But I sort of wanted to just demonstrate that dramatically, okay? So what we're really going to have is we're going to have, so let's go ahead and let's sort of set up our equation. Let's take the square and put it to the other side and make it a square root. So actually, maybe I'll write it out symbolically then. P is equal to the square root of 4 times pi squared times a cubed over g times the mass of the Earth. And now I'll write it out once again, this time substituting in my values. Make a nice big, neat square root. Nice neat division bar. 4 times pi squared. I'm going to put parentheses here. So 6.8 times 10 to the 6 meters cubed divided by big G, 7 times 10 to the minus 11 meters cubed per kilogram per second squared, times the mass of Earth, 6 times 10 to the 24 kilograms. Okay, you guys have learned how to punch this kind of thing before. Let's see if you remember how to do it. That's sort of what this lab is all about. Can you guys punch that up and get me a good answer?
Brendan.
Yeah. That's right, Joel. You got it.
Good. I squared and cubed and divided all where I was supposed to. For once.
Yes. It's very hard to get this right the first time. How about the rest of you guys? Cam, you've got to square root it. I'm afraid to stop sharing because you see it's once you stop sharing, it's sometimes hard to get it back. Rory, correct. Cam, correct. Petrabel, correct. Or Petrabel, correct. Noah, correct. I should hide. Matt, you want to show me? No good, Matt. Henry, what you got? Correct, Henry. Adam?
Whoa, Jake.
What's going on?
I don't know. He got something to the 40th power.
Oh, geez. That doesn't sound right. Sorry, Andrew. Okay. We better all punch this together here because ain't looking so good. Okay. Watch and learn, kids. Okay. 4 times pi squared times 6.8 exp6. We got to cube that, so we're going to go shift, and then here's cubed. Divide by g, 7 exp negative 11. Divide by 6 exp 24 equals, and then we got to shift and square root. What's my final answer?
I'm so lost because I lost you on the part to divide. I lost you on the square.
All right. Okay.
Wait.
Wait. Did you lose me on the part to divide, or did you lose me on the square?
I lost you on like the parentheses square,
There's no parentheses.
that part.
You don't plug in the parentheses.
I meant the square, just the square.
There is no square. There's only a square root or a cube.
The three at the end.
That's called a cube. Okay.
Oh, cube, not
Andrew,
square.
let's try it one more time. I'm sure someone else could benefit from this as well.
Alright.
All right, you ready?
Yeah.
All right. Okay. 4 times pi squared times 6.8 exp6. We have to cube it, so we hit shift and then cube. You with me?
I'm with you.
Divide by 7 exp negative key 11.
Yeah.
Divide by 6 exp 24. Then equals, and then we have to square root. So we do shift, square root.
Yep, I got that.
Good. What should I round it to, Andrew? 2 sig figs.
55.
No, that's a 3 there. You can't make this a 5 if that's a 3.
Oh yeah, I just saw it. Okay, so.
So Andrew,
Hmm.
give me a number.
Is it 50? Is it 50? No, it wouldn't be.
Wait, you got to talk to me here. I'm not sure what you're thinking.
Is it 50, 56 maybe?
No. Look, Andrew, these are your first two digits. This digit and that digit.
Mhm.
Everything else is a 0. Okay. If this number is less than 5, you leave the 4 alone.
All right.
This becomes
Oh,
5.
so you
4.
What are the units, students?
kilograms?
Nope. Kilograms cancel.
Or no, that crosses out. That cancels.
Seconds.
That's right.
Oh, what is
Meters cubed cancel meters cubed, and the square root of seconds squared gives us seconds. How many minutes is that, students? What's the conversion to go from seconds to minutes?
Oh, I know that.
90
Alright,
minutes.
So, it would be 1 minute 60 seconds.
And that, someone pointed out, is 90 minutes. That's how often the ISS goes overhead. Does that mean I can see the ISS every 90 minutes? What do you think? Could I see the ISS every 90 minutes?
No.
Why not, Joel?
Whoa.
Sorry. Why can't I see it every 90 minutes, Joel?
It doesn't fall. This is a tilt of the earth and the time of year.
Not the tilt of Earth. It's a much simpler explanation, a very easy explanation. Here I am on Rhode Island. The ISS travels around the Earth in 90 minutes. Why can't I see it every 90 minutes?
Because it's not always in the same position.
Relative to what?
Your position.
Yeah, because Earth is moving, right? Earth is spinning, and it takes 24 hours, which is a lot longer than 90 minutes. So on the next orbit, it only moves a tiny bit. You've got to wait until you rotate underneath the orbit of the ISS for you to be able to see it, which only happens every couple of days or so. Before I show anything else, can I just make sure everyone's got all this? Do you guys have all this?
I get it for just 30 seconds.
Yeah. Hold on, let me just try to hold this steady. Someone's dog is having a drink.
That's Fenway. Speaking of pets, how's yours?
Oh, my pet raccoon is great. I fed him some raviolis the other day, and he was a very happy camper. I wonder if I have.
Oh, don't do it, Brendan. Don't do it. Oh, you did it. You lost it.
What? Oh.
Your screen share.
Oh, yeah. Well, it's not that. It's, wait, so pause, share.
Maybe if you emptied your email, you wouldn't have so much space taken up on your phone.
Wait, so if I pause, If I pause share, you guys can still see my phone, right?
Yes.
You have more emails than me.
I gotta fix that. What I couldn't remember was what the hell was in my what was in my photographs. Okay, nothing that incriminating. So I want to talk to you guys about the ISS more than this, but let's mess around for a second. Okay, fine. Here's my pet.
Oh, really? Yeah, I bet he didn't like that. But I bet you want some raviolis, don't you? You want a big old... Oh, let's give you a monster chunk. You want a monster chunk? Yeah. Look at that. It's going to make you fat.
That's my pet. Buff lives in the sewer. Anyways, so guys, let's just talk before we end here, because we're making real good time. Let me just show you a couple of things about the ISS that I think is interesting, since it's kind of the point of our story today. There's a cool website that NASA runs called Where is the ISS? And you can kind of live track the ISS from your location. And that's kind of cool because you can sort of figure out like when it's going to be overhead. A couple of these astronomy apps actually have updates. Oh, actually, guys, during the course of this lecture, the International Space Station passed over our heads, but unfortunately we weren't able to see it. Oh no, I'm sorry. This is plus 1.5 hours. It passed over the Midwest, but an hour from now, sorry, the yellow is minus 1.5 hours. The white is the next 5 hours. So it did go over our heads during the course of this lecture, and its next pass is going to be over the Midwest. So I don't know if that means we can see it or not. Usually you can like, why is the space station up there? If you want to know when it goes overhead, I think you can just type in your latitude and your longitude.
Oh, right there, the second one down. That might.
Yeah,
that
I
might
think.
give.
I was looking
maybe
for
not.
one where you plug in your. You have to plug in your coordinates. Well, if you poke around in here, it'll tell you where you can look it up. I have an app called Night Sky, which tells you when the ISS comes overhead, and it gives you alerts. So that one's kind of cool too. I want to show you guys something else that I like. On YouTube, there is a really cool video called Orbit, A Journey Around the Earth in 4K. Orbit. I love this video because you can basically watch a complete orbit from the ISS. So, okay, let me backtrack here. I'm moving a little slow today. On the International Space Station, there's all kinds of cool things to do. So the ISS cupola. When you have some downtime on the ISS, when you're not doing your experiments, you can spend some time inside of this observation window called the cupola. It's kind of like being in 10 Forward in Star Trek or something. You're kind of sitting here looking out the window, and you can kind of watch the Earth rotate underneath you. And it must be really beautiful to spend some time floating there and just looking down at the Earth underneath you. And you can see in this photograph here, people like to spend time doing, well, I would call it astrophotography, but it's really Earth photography because you're getting some cool pictures of the Earth. And they have this great 4K orbit. That's some cool space music, which I'll mute for now. And you can basically just imagine that you're sitting there inside of the cupola on the ISS, watching the Earth rotate underneath you in real time.
It looks like you're the one that's moving for some reason.
Right. Well, you are moving, but it looks like you're stationary and Earth is moving, is maybe what you meant. It's really cool to see this in 4K because there's so much detail. I don't know if it's getting compressed over the Zoom call, but I recently got a 4K projector and it looks so rad. putting this up on my 4K projector and I'll just sit there and eat dinner and just watch Earth rotate underneath. It's especially beautiful when it gets to the night. It's a fun game to try to figure out like what parts of the world you're floating over. Like this is the Red Sea and you can see the Nile River there. It's very beautiful when you see it at night and you can see the lights from all the different cities spread out underneath you. And you really get a sense of how human beings are kind of like this kind of electricity eating monster that's spread itself across the earth. If you were to look at the earth from the daytime, you would not see any structures. You can't see the Great Wall of China. You really can't see anything to show you that there is intelligent life there. But as soon as nighttime hits, it's immediately obvious that intelligent life lives on this planet because the planet is glowing from these rivers of electricity. We're sort of like a cyborg virus that's living on the surface of the planet or something. Anyways, check that out sometime. There's a couple of different versions of this on YouTube, but they're all real good. In any case, I hope you go out and look for the ISS going forward from here, because with a simple app or just by plugging in your latitude into that website, you can find out the next time it'll pass overhead. Okay, I think that covers us for today. It was just a short little lab where we practice using the NK3 formula. Remember that the moral of the story is convert to MKS units and make sure you have the right A and the right mass. Besides that, it's just about plugging it in a few times to your calculator to make sure you get the sequence of buttons right. Okay, do you guys have any other questions for me or anything you'd like to talk about?
That's our lab for today.
That's our lab for today, short and sweet, okay? We'll do chapter 5 homework on Wednesday, okay, guys? And we'll have another lecture on Wednesday. After that, remind me, if you guys can think of it, those of you who are always here and sharing with me, thank you very much. Could you remind me to make a reminder to the class about Monday being a holiday? I could see a few people forgetting that, okay? All right, I'll see you guys on Wednesday. Take care.